Hello, in this video I'm going to show how to solve the Alice and Bob leaving town problem. So the problem states that Alice leaves town at velocity VA, for V Alice, and a time later, time capital T later, Bob leaves town at a higher speed of VB. And they're going to travel in the same direction. How far will Alice have traveled when Bob catches her? Okay, so there are many ways to solve this type of problem. A good starting point is to draw a picture. In particular, I'm going to draw a little plot. I'm going to draw a plot of position x versus time t. So I'm going to call zero, time of zero, when I guess Alice leaves town. If we plot her position versus time, it's a straight line like so. Bob, we'll put him in blue. He leaves town at some later time and catches up with Alice. Okay, so this is this, and here's when he catches her. This period right here, that is while he is waiting, or before he leaves town, that's capital T. And we want to know the distance. We want to know basically that distance. So distance Alice travels also happens to be the distance Bob travels. Okay, so you can potentially do this problem using geometry and slopes and things like that. It's not how I'm going to approach it here. I'm going to approach it by using distance equals rate times time, or the definition of velocity that we've talked about in class. So we've talked about in class, velocity is distance over time. This is true for Alice. This is true for Bob. They just happen to have different velocities and different amounts of time. So I'm actually going to write this as V Alice equals x over t Alice, and V Bob equals x over t Bob. I could put x Alice and x Bob, xa and xb, but it's not necessary because they travel the same distance, so I'm just going to call that distance x. Ta and tb are the times that Alice and Bob spend traveling. So if we draw on our picture, the entire time Alice is traveling, so the entire time, that's Ta, whereas tb is just the time Bob spends traveling. And from the picture, or just using general logic, you can deduce that Ta, the total time, Alice is walking the whole time, is T, what time Bob is waiting to leave town, plus T Bob. Okay, so you might notice that there are 3 equations here and 3 unknowns. So we're good. What are the unknowns? We don't know x. That's what we're looking for. We also don't know Ta and Tb. We know Va and Vb. We don't have values for them, but we're told Va and Vb. So presumably we would know these things. And we know the pause time, capital T. So we want to be able to write x in terms of Va, Vb, and T, capital T. So we need to eliminate little ta, little tb, and solve for x. Okay, so let's see, how can we do this? Well, I'm going to let's eliminate ta first. So if we use this equation here, we can solve it for little ta. We can write ta equals x over va. Similarly, we can use that, solve for tb is equal to x over vb. We can then plug those in to there and there, because we want to eliminate ta and tb, so we're left with x in an equation with other known values. when we do that, we get x over VA is equal to t plus x over VB. So if you plug those in, you get that there. Okay, so now we're down to one equation. We know t, we know v. Ooh, I missed a subscript. That should be VA. VA. We know VA, we know VB. Now we're just looking for x. So we need to solve this equation for x. We need to get x on one side of the equation by itself. Okay, to do that, I'm going, well, this term over here has an x in it, so I'm going to move it over there, and I'm going to get x over VA minus x over VB is equal to t. So I'm getting closer. I've got all the x's on one side, but they're not alone. I have to get everything else to the other side. So I'm going to pull x out of both of these terms have an x in it, so I can pull the x out like so. It's the opposite of the distributive property. Minus 1 over VB is equal to t. I almost there. I've almost got x by itself. I just need to divide both sides of the equation by the thing in parentheses. X is equal to t over 1 over VA minus 1 over VB. This is the correct answer. I can check this by checking the units. Let's check the units. So the units, well, first of all, I'm going to circle it. And then I'm going to check the units. Let's check the units in purple. So the units of a time are seconds. The units of velocity are meters per second minus 1 over meters per second. If you have 1 over meters per second, that becomes seconds per meter. So the bottom comes up into the top. So it becomes seconds per meter, seconds per meter. These two are subtracted from each other. You subtract two things of the same units. It's good. You can't subtract things of different units. You can only subtract things of the same units. So the net units of that is just seconds over meters. Once again, we can flip the fraction again. Meters can go up to the top, and the seconds can cancel. So that has a units of meters, which is good because, well, the answer is a distance, so it better have units of meters. Okay, so check, the units work out. Okay, so that's the units. So I'm just going to leave this as written like this. So that the units work out. I would note that you could also write this answer by multiplying top and bottom of the right-hand side by VA times VB. You can also write this as VT, VA, VB over VB minus VA. These are algebraically the same thing. You know, this answer here and this answer here are algebraically the same thing. Some people like the bottom one better because it's more compact. But either one is an acceptable solution. So this has been the solution to this problem, and we've shown both how to solve for this distance and how to check it using units. Thank you, and have a good day.